Hello everyone, welcome you all. So in this video we are going to derive the expression for efficiency of Otto cycles. As we know, there are four processes in the Otto cycle. The first one is the adiabatic compression or isentropic compression. Second is the heat addition at constant volume, and third is the adiabatic expansion or isentropic expansion, and fourth one is the heat rejection at constant volume. So what does it means? So I will just glance over this four process. So consider this is our engine, so this is our piston, and this is our connecting rod. So this is top dead center, this is bottom dead center. So now initially the air fuel mixture will enter into the cylinder and the piston will be in the BDC position. So first one is the adiabatic compression, means what? Now the piston will move from first process BDC to TDC by compressing the air fuel mixture. Okay, so by compressing the air fuel mixture, the piston will move from BDC to TDC in first stroke or first process. Now when the piston is here, we will provide heat at constant volume, means we are providing heat. So it is Otto cycle, our petrol, gas and other oil engine will work on the Otto cycle. So we are provide spark here, we will do spark plug. So with the help of spark plug we will provide the spark which burn the air fuel mixture. Okay, now the piston will move from again TDC to BDC and it will follow the adiabatic expansion law where the work done by the system. So third stroke is the power stroke, also known as power stroke. Why? Because the work done in third stroke where the piston will move from TDC to BDC by doing some external work. Okay, that work again is transferred from connecting rod to connecting shaft. Okay, now for the heat rejection at constant volume, again the piston it is at BDC. Now the piston will move from BDC to TDC by expelling all unburned gases through exit valve. All the unburned gases will expelled out. The fourth is the heat rejection at constant volume. So it is about the basic four process. Now what we will do, we will try to represent this four process in PVTS diagram. So before going that, we should know some basic about the graph. For example, if I draw a straight vertical line in PV diagram, this pressure volume curve. So if I draw a straight vertical line, what does it means? It means that the volume remains constant. Okay, the volume remains constant even though we are varying the pressure, the volume remain constant. Okay, so in PV diagram, if you draw a straight vertical lines, it means it is the constant volume line. So for example, in TS temperature entropy graph, if I draw a straight vertical line, it means that entropy remains constant even though the temperature is varying. Similarly, if I draw a horizontal line, what does it means? It means the pressure remains constant even though we are varying the volume, the pressure remains constant. Similarly, if I draw in TS diagram a horizontal line, what does it represent? It represents the constant temperature line. Okay, other than in pressure, constant pressure volume, there is a something like that, like this curve or like this. What does it means? It means that the pressure and volume both are varying, but this two follow some other law. Okay, it is neither pressure constant nor volume constant. Similarly, if I draw like this curve, means it is neither temperature entropy constant line, it follows some other law. Okay, so now coming to the Otto cycle. So now here is state 1, initially P1 V1 T1. Okay, from state 1 to we are going to state 2. How we are going? By adiabatic compression. We are going to adiabatic compression. So in PV diagram it will shown like this because it is neither pressure constant nor volume constant. That's why we are showing like this. Now heat addition at constant volume, where the what is constant volume? So I can write straight vertical line. Why? Because it is the 2 to 3 process is the constant volume. So the 1 to 2 process is adiabatic compression and 2 to 3 is heat addition constant volume. And now 3 to 4 here is adiabatic expansion. The adiabatic expansion or adiabatic isentropic expansion is shown in PV diagram like this. This is the 3 to 4 process. Okay, again 4 to 1 is heat rejection at constant volume. Constant volume can be shown like this. Okay, now I will just this is the PV diagram for Otto cycle. Now similarly in TS diagram, again it is adiabatic compression or isentropic compression. So I can write straight vertical line. Why? Because the entropy remain constant from 1 to 2. Now 2 to 3 is constant volume. In TS diagram it is shown like this. Okay, this is 2 to 3 process. Again 3 to 4 is adiabatic expansion or isentropic expansion. It will shown like this because it in here entropy remain constant. Again 4 to 1 here is heat rejection at constant volume. So in constant volume curve can be shown like this. This is the representation of Otto cycle in PVTS diagram. Okay, so this represent this represent the swept volume. We know what is swept volume. Okay, the volume covered by the piston. Okay, this remaining part is the clearance volume. We will write VC. Okay, now from here to here it will be the total volume. We can write swept volume plus clearance volume. Okay, now this V1 by V2. V1 by V2 is nothing but compression ratio. Okay, V1 by V2 is known as compression ratio. Similarly, V4 by V3. V4 by V3 is known as expansion ratio. Okay, now you can see here V1 is equals to V4. Okay, it is vertical line, and here also V2 is equals to V3. So in Otto cycle, this compression ratio and the expansion ratio both are same, so I can write R. Okay, in Otto cycle the compression ratio and expansion ratio are same. Now what we have to draw the efficiency. What is the efficiency for output by input? So what is output here? So now just one more glance over. In 1 to 2 process, it is adiabatic compression. Compression means what we will do, we are giving work, okay, W in, because it is a compression process. To compress, the piston will move from BDC to DC, we have to give some work. Okay, now heat addition. So in 2 to 3 process, what we are doing, we are supplying heat or we are adding heat, so I can write heat added. Okay, 3 to 4 is adiabatic expansion. Expansion means the work done, your work done in 3 to 4 process. And for heat rejection, it is heat rejected. Heat is rejected. So this is the 4 basic process in the Otto cycle. So efficiency is output by input. So what is output here is nothing but work done. Output here is work done divided by input. What we are giving, heat is supplied, heat added, or I can write heat supplied. Heat supplied. So this is my equation number 1. So now what is heat supplied here? How we will calculate heat supplied? So we already discussed in first law of thermodynamics. The heat supplied is written at mCV. Why? Because it is constant volume mCV in 2 to 3 process. So I can write T3 minus T2. If I consider 1 kg of air, so this will be CV T3 minus T2. Okay, so now work done, I need to calculate work done. How will calculate work done? Work done is nothing but heat supplied minus heat rejected. Okay, so what is heat supplied? Again CV T3 minus T2 minus heat rejected. Heat rejected in 4 to 1 process, so I can write CV, and it is also a constant volume, so I can write T4 minus T1. Okay, if I take CV common from that, so what I get, this T3 minus T2 minus T4 minus T1. Okay, so if I substitute here, what I get, efficiency is equals to work done. What is work done? CV is T3 minus T2 minus of T4 minus T1 divided by heat supplied. What is heat supplied? CV T3 minus T2. The CV gets cancelled out. So if I split the terms, what I get, this T3 minus T2 divided by T3 minus T2 minus of T4 minus T1 divided by T3 minus T2. This to get cancelled out, left out with 1 T4 minus T1 divided by T3 minus T2. So this is the efficiency of Otto cycle in terms of temperature. Again I have to convert this in terms of compression ratio. So what I will do now, I will erase this. So now if I consider here 1 to 2 process, so 1 to 2 process is nothing but the isentropic compression or adiabatic compression. So I can write this relation T2 by T1 equals to V1 by V2 whole to the power of gamma minus 1, where gamma is the adiabatic index. So we already derived this relation if the process is adiabatic. So I will provide link in the description. If you want to watch how this relation came, you can watch it. Okay, so now here V1 by V2 is nothing but compression ratio, and which is equals to R. So you can I write T2 by T1 equals to R key power of gamma minus 1. If I bring T1 that side, it will be T1 R key power of gamma minus 1. Okay, so this is my T2. Similarly, now 3 to 4 process I take, because this is also the adiabatic or asymptotic process. So I can write from here T3 by T4, which is equals to V4 by V3 whole to the power of gamma minus 1. Again, V4 by V3 is nothing but expansion ratio, and which is equals to R. So from this relation I can write direct T3 is equals to T4 into R key power of gamma minus 1. This is my T2 T3. If I substitute over here, what I get? Now this efficiency is equals to 1 minus T4 minus T1 divided by T3. In the place of T3 I can write T4 R key power of gamma minus 1, this minus, and T2. In the place of T2 I can write T1 R key power of gamma minus 1. So in the denominator I can take R key power of gamma minus 1 constant. So I left out with T4 minus T1. So this will cancel out. Now efficiency here 1 minus 1 divided by R key power of gamma minus 1. This is the efficiency of Otto cycle in terms of compression ratio. Okay. So now here you can see from expression, if we increase the value of R, the efficiency of Otto cycle will also increases, because it is in the power here negative is there. So if we increase the value of R, okay, so now the value of efficiency also increases, but due to practical difficulties, the compression ratio R is limited to only 8. Okay, so this is about the efficiency of Otto cycle. Thank you.